Now we're going to look at how we can compute probabilities in terms of independent events. Where it's important to bear in mind here that unlike when we were looking at things with the addition rules in the earlier sections, we're looking at either or. We're not saying how do we get a situation where this happens or that happens. We're talking about both. So we're talking about two things happening rather than just one. And for this, if we want to get the probability of A and B, where they're independent events, one does not affect the other, you just multiply the two events. PA and B is equal to PA times PB. And to understand this, we're going to look at a few examples. Where for our first one, we're going to look at finding the probability of tossing a coin getting heads.
What's the most you ever lost on a coin toss? Sir?
And then rolling a die and getting a 6. Where here there's not too much to what we have to do here. If we want the probability of getting a head and rolling a 6, what we need to understand here is we're looking at the probability of getting a head times the probability of getting a 6, because presumably these two things don't affect each other in any way. So this would just be 1 out of 2 for the coin flip times 1 out of 6 for the dice roll. So in total, our probability would end up being 1 out of 12. Not too hard to get that one. For our second example, we have that ACL reconstructive surgery has an observed probability of success of 95%, where we want to find the probability that 3 surgeries are successful, along with looking at the probability of getting 1 out of 3 as a failure. So in our first case, presumably each surgery doesn't affect the other. It's maybe not the fairest assumption that a surgeon might get more confident if they do their job really well the first couple times, or they might get less confident if they made a silly mistake on one of them. But we're treating these as independent because we'd like to think that a surgeon's performance isn't affected by previous attempts. So here, if we want to get the probability of 3 successful surgeries, really all we have to do is extend our idea of independence to 3 cases. The probability of 3 successes is just the probability of 1 success and another success and a third success that I don't really have the space for on here, but I think you get the idea. So if we want to find the probability of all 3 succeeding, you just multiply the 3 probabilities together. Which would give you a total probability here of about 0.857. Now on the other hand, if you want to get a bit more of a pessimistic outlook, if you want to see the probability that at least one of them will fail, well, in this case, what you'd have to understand here is at least one failure would be 1 failure and 2 successes, kind of a clunky case, then 2 failures and 1 success, another clunky case, or 3 failures. A negative case, but it's not that hard. Long and short of it is you got 3 different options that can satisfy this. So you need to do a lot of anding and a little bit of oring, or in other words, a lot of multiplying and some addition too. But instead of thinking about it that way, it can actually be a lot more efficient here to think about this in terms of a complement, because the opposite of at least one failure is going to be that none of them fail. That is to say, probability of 3 successes, which we just got up there. So if you want to find the probability of at least one failure, you can either go through a whole bunch of cases, or we can just use the complement, which will give us that our probability is 1 minus 0.857, or 0.143.